Today's lesson is kind of a review of something from Algebra 2, but it will really help us in our content for pre-calculus in the coming sections, and that is how to solve rational equations. Now remember, rational equations, which is one of the basic parent functions we studied, are rational equations that can be written in this form, where the numerator is a function and the denominator is a function. So it is not a rational equation unless there is a variable in the denominator. If there's just a number in your denominator, then that's just a scalar that you're multiplying by. So we're having functions that have functions in the top and functions in the bottom. Now, sometimes when we solve rational equations, we get extraneous solutions, which are solutions that are not really actual solutions to the original equation, which means that we have to check each solution that we get to ensure that it is not one of my extraneous solutions. But remember, for rational equations, restrictions to the domain, which include our extraneous solutions, are found when the denominator of the original equation is equal to 0, because you can't divide by 0. So we have to remember at the very end when we solve that we think about our restrictions on this particular function. So if we're looking at this first question, we want to solve for x. Okay, the problem is that there is an x on the left side and the right side, and on the right side it's in the denominator. So to be able to actually compare these equations, I need to multiply them so that they have a common denominator. Okay? That's how we are able to deal with rational functions. So if I wanted there to be a common denominator between these two functions, I know that the denominator on the right side is just x, and originally the denominator on this side is just 1. What would I have to multiply the denominator on the left side to be able to get it to be x? Well, very obviously, you multiply it by x. Well, what I multiply in the bottom of the denominator, I have to multiply in the top. So I'm going to choose to multiply both the top and bottom by this denominator of x. And now I have a common denominator. And once I have this common denominator on the left and right side for all pieces on the left and right side, I can kind of ignore the denominators and just take the numerator itself and set them equal to each other. Okay, I know how to handle a question like this. This is x squared plus 5x equal to 14. And if I move that 14 to the left-hand side so that it's equal to 0, I see now that I've gone from a rational equation to a quadratic equation. And a quadratic equation we can solve with factoring or with the quadratic formula. So we're going to factor this one. There would be an x and an x in the front. I'm looking for factors of 14 that end up adding to 5. The factors of 14 are 1 times 14, so we're going to try those. This would give me 14 and 1. There's no way I can make 5 out of 14 and 1, so I try something else. You have also 2 and 7, which would give me 7 and 2. But I can make 5 out of 7 and 2 if I have a positive 7 and a negative 2. Okay. Great, well I factored it. If we go on to solve step, we know that x is going to be equal to 2 and x is going to be equal to negative 7. Here are my solutions that I find, but I have to go back and check the original restrictions of this graph. The original restrictions of this graph are that the original denominators, any of the original denominators, cannot be equal to 0. So since I have an original denominator of x, I'm going to say that one of my restrictions in this particular equation is that x cannot equal 0. Did either of our solutions equal 0? No, so both of them are okay, and we have two solutions to this equation. Now, that's a very simple example. But if we see a more complicated example, we're actually going to start thinking about the restrictions first because it actually probably helps me solve the entire question. Okay, so we know that my restrictions, which I will list over here, to this equation that I'm trying to solve are anywhere the original denominators would equal 0. So I know that x cannot equal negative 5 from this first domain. from this first denominator, sorry. We know that x cannot equal 2 from the second denominator, but right away, I can't tell right off the bat what this denominator would be set equal to when it's solved for 0. So I'm going to need to factor that first one, but I'm going to rewrite the entire problem just so that I have a nice, neat paper. You should probably do the same. So I have the same left-hand side, and then the right-hand side I would just factor to x plus 5, x minus 2. And wouldn't you know it, we already have these two factors and their zeros as a restriction, because x cannot be negative 5 and x cannot be 2. So these are my only restrictions for this particular rational equation. Okay, I need, again, all three terms to have the same denominator. Very obviously, this one is the biggest denominator. Okay, I need these two denominators to match. What would I have to multiply this first part by so that it had the same denominator as this one? Yeah, hopefully you noticed that if I multiply this first denominator by x minus 2, that it will then have the same denominator as the right-hand side. Further, if I multiply the second part of this by x plus 5, top and bottom, do you see that now all three pieces have the same denominator? Fabulous. That's what we want. Oh my gosh, I've made a mistake here. Did anybody notice that I just totally dropped this x off of here? My bad. Okay, great. Now that we have matching denominators, we really only care about the numerators, which would be 3x times x minus 2. I'm just rewriting this. I know I could be distributing right now, but I'm just going to rewrite it. X plus 5 equal to 7. This is now just the numerators. Since all of the denominators match, we can essentially ignore them because we're only solving for the problems that are not equal on the top. Well, if we distribute, this is going to be 3x squared minus 6x plus x plus 5 equal to 7. We want to solve this now quadratic equation, so I would combine like terms. This is going to be minus 5x, and then if I move the 7 over, this is going to be negative 2, so 5 minus 7 is negative 2. And if we factor, this would be 3x and x. We're looking for factors of 2 that end up being 5. Well, the only factors are 1 and 2, so we'll try this direction first. This would give me 6 and 1. I can make negative 5 out of 6 and 1 as long as I have a negative 6 and a positive 1. Therefore, I can say that my solutions, let me just back out a second. My solutions here using the zero product property, solving the first equation is going to be minus 1 divided by 3. So negative 1/3, and x equal to 2. Thanks, zero product property. Fabulous, so those are my solutions. But remember, we have to now check these solutions versus what we knew was a restriction or an extraneous solution from the get-go. And we already said that x cannot equal to 2, so we're just going to cross that one out and remind ourselves that that was extraneous, because it was in my list of numbers that x cannot be equal to from the original denominator. Fabulous. Let's see another example here. So we want to solve, backed up on me. We want to solve this rational equation. First thing we think about when we have a rational equation is that, hello, denominators cannot be equal to 0, so we have some restrictions. Since we have a denominator of x minus 4, we're going to say that x cannot be equal to 4 because that would make that denominator 0 and thus basically break this function. But we also need all of the sides to have a common denominator. Since these two sides technically right now have a denominator of 1, I need to multiply both of them by the denominator x minus 4 so that I have a common denominator amongst all of my terms. And yes, I do realize that I'm multiplying 0 by x minus 4, but I'm just showing you that this is exactly what we're doing each time. We're getting there to be a common denominator, so I can actually add or subtract these things, which is what fraction rules tell me. So this means my numerators would be, and yes, I'm writing this step sort of unnecessarily. I know that you can distribute probably in one step, but I wanted to show you. Here's all of my numerators. And then we can distribute. This is x squared minus 4x plus 1 equal to 0. We want to solve this, so my gut instinct is to try factoring. I hope you're writing with pencil. If you're writing with pen, don't do this. So we're going to try this. We want all the factors of 1, which are only 1 and 1, but is there any way I can make negative 4 out of 1x and 1x? No. So we have a problem. And this is not actually factorable the way we've learned how to factor. And luckily, it's a degree 2 polynomial, so we don't have to get into all of the synthetic division and all of the remainder theorem things that was in the last unit. We can just go straight to that quadratic equation. The quadratic equation, and I'm going to sing it for you, is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Nailed it. So we fill in the quadratic formula, and then we start reducing. Negative 4 is positive 4. Negative 4 squared is 16. 4 times 1 times 1 is 4. All over 2. This is going to be 4 plus or minus the square root of 12 over 2. And if you keep going, you would remember that 12 actually factors out to 2 square root of 3 over 2. And if you're like, what, Miss Quigley? 12 is 2 times 6 and then 2 times 3. And if there's a double pair in a square, it gets to pop out, and all of the leftovers stay underneath the radical bar. Finishing, simplifying here, 4 divided by 2, since that's the first part here. 4 divided by 2 is 2, and then 2 square root of 3 divided by 2 is just 1 square root of 3. So here are my two solutions. Now I have to make sure, again, that they're okay for my restrictions that I started with, but my only restriction was that x could not be x could not be 4, and like, this is not 4. This is 2 plus or minus the square root of 3. So both of these solutions check out, and I'm okay. So the gist of this is, whenever you get a common denominator, you set the numerators equal to each other, so we only deal with the numerators, and solve as necessary. It may be factoring, you may have to complete the square, you may have to use the quadratic formula. Just for yourself, since these are your notes, if you do not know the quadratic formula, remember it is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. That might be something we need to memorize ASAP. If we move on to the next question, we see that there are 3 terms in this rational equation, 1, 2, and 3. We need all of them to have a common denominator, and we need to set up our restrictions. So that's what we're going to do first. We're going to list our restrictions. And we're going to do this first because it's going to remind me that I need to factor each of the bottom equations so that I know what x cannot be equal to. Very obviously, the first term has x plus 2 as its denominator, so x cannot be equal to negative 2, or else it would be 0. For the second term, we don't know yet exactly what x cannot be equal to because it's not properly factored. But it just has a GCF of x, so if you take one of those x's out, you will see that its denominator is just x and x plus 2. So we know that x cannot be 0, otherwise that denominator would be 0, and again that x cannot be negative 2 for the second part. The third term here says that x cannot be equal to 0 either, which is already part of my restriction. So I only have 3 numbers that x cannot be, or that would be an extraneous solution if I got it as one of my solutions to the equation. Since I want them all to have a common denominator, this first term, and I'm going to kind of do this problem differently to show that this is exactly what we're doing, having a common denominator. I want the denominator to be x times x plus 2. Well, this second term here already has that denominator, so nothing needs to change about plus 6. But the first term only has a denominator of x plus 2, so which factor is it missing? X. So I would be multiplying that just simply by x. In the second part, I want the denominator again to be x times x plus 2. Its denominator already is just x, so what am I going to have to multiply it by? What is it missing? It's missing the x plus 2. Once I have common denominator on the left side and the right side, I can deal solely with the numerators. This is going to be 3x plus 6 equal to, and again, I know I could probably multiply this step out and save a line of work, but since these are your notes, I want you to see what's happening here. Let's go ahead and FOIL this out. If we multiply 3 times x, we get 3x. 3 times 2 is 6. Negative x times x is negative x squared, and negative x times 2 is negative 2x. I'm going to simultaneously combine like terms and move all of the numbers to the other side of the equation so that they're on the left. So I would be adding x squared to both sides. If I combine all of my x's, these would end up canceling. Sorry, I don't know why that line stayed there for so long. These two would end up canceling, and I would be adding 2x to both sides. And then if I moved all of my constants to the same side, these 6's would end up canceling because it would be 6 minus 6. So that is equal to 0. Now to solve this equation, hopefully you notice that this is just a GCF of x times x plus 2. And so if I use the zero product property, I'm saying that x is equal to 0 and x is equal to negative 2. Those are my two solutions that I got from solving the rational equations. However, we have to remember that we have some restrictions on this type of function. The denominators cannot be equal to 0, and we said earlier that my restrictions are simply x cannot be equal to negative 2 and x cannot be equal to 0. So like, both of these I would end up getting rid of because they're both extraneous. So this would actually be no solution. Now these 4 questions on the back are kind of going to be the like you do part of the notes. I'm going to go through them one by one, but I'm just going to have the solutions appear for you. So I actually want you to pause the video here, and I want you to stop and try number 1, and then we'll do number 1, and then stop and try number 2, then we'll do number 2, and on to finish all of the page. So if you finish this one, it should be x equal to 3 and x equal to 1, and both of those are fine. Neither of them are extraneous. The way we would do this, first of all, we found our restrictions by setting any original denominators equal to 0 and solving, which in this case means x cannot be 0. We then want all of the terms to have a least common denominator, which means we're going to multiply 2 of the terms by x so that I can deal only with the numerators. Then I set equal to 0, and I factored, and I was able to use the zero product property to be able to say that x is equal to 3 and x is equal to 1. Again, both of those work because neither of them are part of my restriction. Let's go on to number 2. Again, you're going to pause the video and try number 2, and then press go when you're ready to see how you did. All right, here is what this one should look like. First things first, we factored the original denominator because we weren't exactly sure what the zeros of that denominator would be. But we found out that they kind of match, so the restrictions are just that x cannot be 0 because it would be 0 in denominator here, and x can't be negative 3 because it would make most of these denominators 0. But now we need the denominators to match, so after we factor to find the zeros or the restrictions of the denominator, we found a least common denominator, which then allows us to only work with the numerators. This was a FOIL step. And then I set equal to 0, so I combined like terms and moved the 6 over. I factored, and then I used the zero product property to get that x is equal to -3 and -1. However, if you answer like this, that will be marked incorrect. Remember, -3 is part of my restrictions, so that's actually an extraneous solution, but -1 totally works. Let's go to number 3, same sort of situation. Pause the video and try it yourself, and then we'll see how you did. Okay, here's what this one looks like. Again, we factor this first larger denominator, the polynomial denominator, because we don't know what its factors are, so we don't know what numbers make it 0. But we simply see that the restrictions for the whole thing cannot be 1, cannot be 3, again, 1 and 3. So my only restrictions are that x cannot be 1 and cannot be 3. So then I just worked on finding a least common denominator for all 3 terms. And once I had that, I was able to work with numerators only. And I did some distribution, and then I combined like terms and set equal to 0. And then I factored. And then once more, the zero product property allows me to say that x is equal to -1/2 and +3. But if you don't forget to check your extraneous solutions and toss out the solution of 3, since it is one of my extraneous restrictions, we would answer 2 solutions, and this one only has 1 solution. Let's go on to the last problem. You're almost there, but same thing. Pause the video, try the problem on your own, press go to check your work. Oops, I messed up a little bit, and obviously you could see the first step. Please ignore and start from here. I will actually pause it this time. Here's the last one. Again, same steps as always. Once we know what our factors are, so we know our restrictions, we're going to find the least common denominator and work then with the numerators only. We would FOIL if we need to FOIL, and then combine like terms as needed. There was nothing to set equal to since it was already set equal to 0. But when I factor and use the zero product property to get to my solutions, I will notice that both of these solutions are extraneous. Those are both the numbers I put in my restrictions, so this solution actually would be no solution.